So in the previous segment, we looked at two ways to superimpose waves. One is really works. The first method that really works the best, probably for just adding two waves, although it can be extended to more than two. And the second method was more like adding vectors, and it was probably a little more general, could, in, especially in working with more than one. Um, Another method, which is really method three, is to think of waves as phasors in a complex plane, essentially. I have an imaginary axis, which is like the y-axis, a real axis, like the x-axis, and any complex number up here can be represented in polar form by a e to the I theta, where a and theta are these angles. Theta is the angle with the real axis, in this counterclockwise sense. And by Euler's relationship, you can decompose this into a cosine theta plus I sine theta. But generally, one it's better to deal with the complex form. But certainly, you can deal with the complex form. Maybe you start with, and like we're starting with a times the sine of something, and I write it as a complex number and then work all the way through, and then ultimately take the imaginary part to get back to the sine. Or if we'd use cosines for our different fields, then amplitudes and cosine functions for our sinusoidal, then we would do all of our calculation in terms of these complex phasors, really, and then ultimately take the real part to get back to the a cosine theta if we'd use cosines here. But what I'm going to do is I'll stick with that sine notation that we had before. So I'll treat these as the real waves from those two independent sources. Again, I'll just do two, but it extends naturally to more than two. So I want to add E1 and E2 that are really real waves. And what I'll do is I'll extend them into this complex phasor notation as the amplitude times this e to the alpha 1 plus or minus omega t for this one, E2 in this complex form, and then the resultant, which I want ultimately to add these, I want the resultant to have amplitude A, which is really what I'm after, and whatever this angle theta is. So I'm really after, again, the resultant amplitude and the resultant angle of these phasors. Again, you may get to the end and get this E here, but once you know all of these things, if you want to go back to the imaginary part to recover these, then you just take whatever your solution is here by the time you get it. You just simply take the imaginary part. Likewise, if these had been cosines, you could form the same phasors and then done your calculations, and then at the end take the real part to get back to this form over here, the real part of E. So now I'll substitute these into the sum, and I get this. This top one is just simply this equation here with all of these things substituted into it. If you look, E1 is just this, E2 is just this, and E is just this over here. So I just substitute these into this equation. And now this next result, what I'll do is I'll take the complex conjugate of both sides. So in this equation, I simply replace an I everywhere by minus I by minus I by minus I. and then I'll multiply this times this. Well, I'll get these two will be inverses, and so when I multiply these two, I'll get a squared. Now, actually, a could be could in general be complex in certain situations. So you could have this as the absolute magnitude of a squared, but for now, think of these as just real. And now then I need to multiply all of this times all of this. And so that's this part here in this square bracket, and then this complex conjugate is here. If I multiply this out, this term times this one, well, these are inverses of one another, so it just becomes a squared. This term times this one, I'll get a1, a2. I'll get a minus alpha here, and a plus alpha 1, or I get a minus alpha 2, but I'll factor that out, so I get a minus alpha 2 minus this alpha 1, and so if I distribute across, then this becomes the minus alpha 2 and the plus alpha 1 from multiplying this term times this one. The other pieces go out, so that's kind of nice. And then this term times this one, again I get a cross term. The only difference is here I'll get e to the alpha, and here I'll get minus, and so this I have an I of alpha 2 minus alpha 1. Again, the other terms get blown away. The part with the omega t, you can go through that. And then finally, this term times this one, again, that gives me a2 squared here. And this times this will give me I alpha 2 minus alpha 1, and the other terms will cancel in the multiplication. So it reduces pretty simply in terms of manipulating the complex values of these things. And the way I've written it, then pretty obviously, delta is the phase difference, so delta is just alpha 2 minus alpha 1. I'll write this term first, so it's I delta, and then this one, that's a delta, so it's e to the minus I delta. So I have that. Again, I can multiply by 2 and divide by 2. And you may recognize this is just the cosine of delta. So there is the addition. You can find the square root. It's a very similar expression that we had before, except we arrived at in this complex notation. Again, just looking at 2. This extends naturally, and in particularly in certain software, MATLAB and so on, to multiply 4 or 5 of these phases together is not much of a chore. The usual situation that we'll encounter in our dealings, at least in this course with optics, is we'll have these 2 waves both having the same amplitude, but they will be coming from slightly displaced situations. So if we look at that particular case, it's a special case, then if you plug all of this in up here, if A1 equals A2 equals A, well, I'll get 2 of them here, so I'll get 2A squared when I combine these two. A1 equals A, A2 equals A, I'll get 2A squared here in cosine delta. And so in this commonly occurring situation, we can factor out the 2A squared, and I'll get 1 plus cosine delta here. And I'll then do the half angle formula, which I never remembered. But I can certainly write cosine of delta is equal to cosine of delta over 2 plus cosine of delta over 2. And I do remember that this is the cosine of the first term times the cosine of the second term, that's cosine squared, minus its flip sine and the cosine of a sum, sine of delta over 2, sine of delta over 2, so sine squared. And then I can replace the sine squared with 1 minus cosine squared. And so minus a 1 becomes here, and minus a minus cosine squared will give me 2 cosine squared deltas here. And then I just add, I'm after this term, so I add 1 to both sides. So if I add 1, or if you like, you can take this one over to this side. And we find that this half angle formula that 1 plus cosine delta, which is this thing in parentheses, is equal to 2 cosine squared delta over 2. And so I'll make that substitution up here. So I get 2a squared, that was what was left. This 1 plus cosine delta is 2 cosine squared delta over 2. Oh, then you can, if you like, you can take the square root of that, square root of both sides. Square root of 2 squared is 2, square root of a squared is a, square root of cosine squared is this cosine delta term. So this one or this one up here. One can substitute in and do a little more interpretation here. And if I look at this delta, remember that's simply the phase difference, alpha 2 minus alpha 1. And alpha 2 was k r2, where r was the distance I was from the source, where our detector is from the source, minus k r2, again r, this r1 is the distance the source 1 is from the detector. And one gets this same expression that we got earlier, 2 pi is k over lambda, by definition, times the difference in the path, the actual physical path that these took. Now, as we saw earlier, the intensity of the light is proportional to the square of the electric field. And that would mean for the square of the electric field, and at least in this average sense, one can square these up here, and the square, the amplitude is 2a cosine delta over 2, and when I square it, I see that the intensity of the light or of the hitting the detector is proportional to the amplitude squared, and the amplitude squared is 4a squared cosine squared delta. And if you like, you can just lump all these proportionality constants together, which is what I did here, into one big constant I. That's I naught. And whatever it is related to the amplitudes at the source and some other fundamental constants here, the speed of light and some other things. So we've lumped all those into a single constant. And then delta, we can put that back in, but delta was 2 pi lambda over delta r. I've got a 1/2 here, and so those halves go out, and I get the cosine squared pi delta r over lambda. Notice it's dimensionless. Delta r is a length, lambda is a length. Now they need to be in the same units, so that's just the difference in the physical path. Number of waves that fit into it, and the pi indicates that all this would, if you use consistent units, this is in radians here. So you see that the intensity is going to be proportional to the cosine squared for these 2 point sources that have the same amplitude, and we'll see how that gets attacked a little later. Notice a few things about it, though. If I look at this expression, well, I'm going to get the maximum intensity when this thing inside here is either 0 or plus or minus 180 degrees, plus or minus pi, or plus or minus 2. All of those, this will become 1 inside it, and the maximum will be I naught of our intensity, and that occurs when this factor inside here, this delta over 2, is equal to these values, or this factor is equal to these. On the other hand, the minimum, well, the lowest it ever gets is 0, and that occurs when this delta over 2 factor here is a multiple of pi over 2, really an odd multiple of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, because then it's 90 degrees or 270. And then you get the cosine of 90 or 270, etc., vanishes, and so the intensity is 0. Well, you can get general expressions for these in terms of an integer m, or here, and they're even delta over 2 is either even or odd values of these factors. But in any event, I'll generally do this many times, but only in specific problems, and we'll just reapply it. Don't remember this in general. This is just pointing it out.